recording. And if you have questions or comments, please post them in the chat so that our speaker can also respond in the chat or during the discussion in the panel at the end of today's session. You are encouraged to discuss online in the social networks, mentioning the 1CG open lecture. And if you see any problem with this open lecture, any technical issue, please contact the host or send an email to info1cg.org. About myself, I already told you that I will be the moderator for today, and I will not speak much. I will leave our speaker speak. The first speaker will be Markus Mueck of Intel, and he will tell us about native artificial intelligence and native computing as key features for 6G. The second speaker will be Marie-Josée Montpetit, professor at the McGill University, and she will tell us about intelligent programmable data planes. Next will be Rocky Baba from NTT-NS Labs in Japan, and he will explain what NTT-NS Labs are doing on in-network service-aware computing for 6G. And finally, last but not least, Professor Calegati from the University of Bologna will explain intelligent user plane innovations for the manufacturing sector. So I think we can move to the first speaker, which will be Markus Mueck. So I invite Markus to start sharing his screen. In the meanwhile, I will
Thank you so much,
introduce.
Riccardo. I think you need to unshare. Yeah, exactly.
Yeah.
Okay.
I will shortly introduce you, Markus. So Markus is principal engineer at Intel Germany in Munich and the engineering director. Moreover, he is chair of the ETSI board, and in ETSI, again, he is also chair of the OCG AI, which is coordinating the overall effort of the organization on artificial intelligence. He's also adjunct professor at the University of Technologies of Sydney, and he also participated to the project XAX, leading the effort on artificial intelligence and machine learning for 6G. So I leave Markus the floor, please.
Thank you so much, Riccardo, for the kind introduction and the invitation. It's a pleasure and honor to speak in this forum. So my talk will be about the native integration of artificial intelligence and compute as key features of 6G, with the objective not only to improve the overall network efficiency, but also to provide new key features to consumers and other types of users. So looking at the evolution over time, I think it is fair to say that communications and compute have been kind of two different animals at the very beginning, right? Not really integrated, while going into 4G, 5G, and now 6G, we are really seeing that ICT and IT are getting intertwined and very, very closely linked. So we are really seeing a convergence of communications and computing. And this is the reason why I believe it makes definite sense to actually look at the network architecture, not only from a communications perspective, but also from a compute and in particular from an AI, ML and data processing perspective. Now, when we look at various 6G technology objectives, here are a couple of thoughts. So obviously, we need to go for a substantial increase of the relevant KPIs for the digital world experience. I mean, joint communication and sensing is a big topic. Energy efficiency and sustainability is a big topic. Cybersecurity, trust, resilience. I mean, these are obvious big topics, but I think it is really important, and this is, I think, a lesson we have seen from 5G. We need to take great care not only to improve KPIs that are important but transparent to the user, but we really need to take care to have a visible and a perceivable differentiation for the end user in the end. And I think this is one of the challenges that we see in the definition of 6G. Now, from the Intel perspective, we really believe that there are certain ingredients that are not only additive kind of features, but they are multiplicative, right? So they're amplifying each other. And this starts from compute over pervasive connectivity, going over cloud to edge infrastructure, artificial intelligence and sensing. So actually all of these ingredients will really be key to create this kind of massive increase of KPIs related to digital experience. Now, when we take a look at the evolution from 4G, 5G to 6G, I think we have been seeing in 4G and 5G that compute, data, and processing features have been very much localized. You know, for example, we can highlight the edge, we can highlight the localization in the data center and cloud, right? But when going now towards 6G, my vision and Intel's vision is that we are really going to see ubiquitous usage of compute, AI, and data processing across the different parts of the network, right? And this is not only within the infrastructure, but really, I mean, you know, going end to end, right? I mean, of course, there will be still storage and processing in the cloud. Of course, there will be still storage and processing in the edge, but we will also see it in user devices. And the challenge will be actually to connect these user devices and actually to define the best like trade-off of doing and performing processing within the devices versus offloading the processes to various parts of the network. So is it better to go to the core, to the edge, to the data center, or should I rather process directly on the device, or even create a federation among multiple devices? Now, when looking at this kind of vision, we basically see various service scenarios that can be envisaged. So let's start on the upper left-hand side. Here we basically have the idea that a mobile user or mobile device itself subscribes to 6G compute services and actually exploits the capacity and the data that is available in the network. On the upper right-hand side, there's a different example. You know, an app provider actually subscribes to such 6G computing services in order, you know, to make an app available that is building on the related resources and infrastructure. On the lower left-hand side, you see that you know, 6G can also provide a basis for services to cloud providers, where, you know, an app is not only executed in the cloud itself, but is actually distributed end to end, starting from the mobile device, going over the 6G network, going through different like infrastructure as a service, software as a service, platform as a service principles up to the cloud. And then on the lower right-hand side, even the 6G network can play a role as a moderator in a multi-cloud scenario. So connecting one app, you know, to different apps located in one or multiple clouds. And again, looking at that from where we are and where we want to go, I mean, in current 5G systems, we have certain functional capabilities, starting with the management functional plane, the control functional plane, and the user functional plane. But we are really only providing a single service, which is a communication service provided through the communication service plane. Now, Now, our vision is actually that we are extending this kind of service that is going to be provided by adding compute services and data services, right? And compute services, of course, also include AI, ML processing services, but not only, can also relate to more generic compute services. And this actually requires changes in the overall architecture. And what's interesting here is that this provides an opportunity to the mobile network operator, of course, to evolve from a situation where only a data pipe is being provided. I mean, to put it in simple terms, to have a much more comprehensive and holistic offering to users. Obviously, then dramatically and enlarging the scope of the business offering. Now, how is this going to be implemented? So our view is that for the time being, most of these compute and data management functionalities are being added basically on top of the networking stack, right? Mainly, on top of layer 7, right? In a way that is almost independent of the design of the network. Now going towards 6G, our view is that it's going to be insufficient. We believe that we need actually to go deep into the network and anchor these compute, AI, ML, and other type of compute features, but also data processing features deep inside the network. And the proposal here is actually to add additional entities on the level of the service-based architecture. And as you can see here, we propose actually to introduce certain compute control plane functions, compute user plane functions, and the same for data. I think an interesting question is here, and I think this still requires additional thinking. Which applications really require this deep integration, and which applications really require, or for which applications it would actually be sufficient to simply put it on top of the stack. Just a couple of thoughts on this, because this is actually a very deep question, and I think it would be very interesting to also receive other views on this. Just to give one example is, I think deep inside the network architecture, you have a plethora of network knowledge that is being available, that is not going to be made available in its entirety to upper layers, right? It would be too complex, it would be too costly, it just doesn't make sense, right? So basically, in order to be able to really exploit the knowledge within the network, or the whole wisdom inside the network, you really need to anchor these functionalities deep inside the architecture. And that is providing then again an interesting, let's say, usage model for mobile network operators, I believe, to use and monetize their data. Because what is happening today, typically data is being considered as the new black oil, right? So to say. So data is being treated like a treasure, and typically people do not want to give away the data, right? So at least not in its raw form. So, but what we are seeing here is, when we are looking at at an approach where, for example, within the network or even external users can come to the network with a certain problem statement and say, hey, based on your wisdom, based on your knowledge, and it can be like radio knowledge, that can be societal knowledge, that can be all type of knowledge available in the network. Can you possibly help me to solve a specific problem? Then what the network, based on this approach can do is actually to use the data and the wisdom that is available within the network to create and optimize an AI model that is tailored to the specific needs of the user querying this solution. And then, you know, this model can be transferred to the user or transferred to other, you know, network entity in order to solve the specific problem. And the nice part about this is, you know, in this approach, the data is being obfuscated within the model. So you don't really give the data away. You give actually somehow the wisdom away, but while keeping the data, the raw data to yourself. The data, the underlying data that was used to create the AI model is not visible, you know, to the consumer of this model. And I think this is really creating a whole new approach on how to exploit the data and knowledge available within a network. Now, what does that mean? It means basically that compute and AI processing functionalities and components are not only localized in one specific entity of the network, like on the upper picture, it is here localized within the cloud computing part, but it's going to be it's going to be put, you know, really end to end. There will be processing entities in the UE, in the RAN, in the core network, everywhere, right? And so each of these processing entity can, you know, for example, exploit compute functions, you know, that are locally available, can exploit compute functions that are, you know, in a remote entity, in a remote location, but can also ask, you know, the remote locations, as I just said, you know, please use your local wisdom in order to create an AI model, you know, that serves my specific purpose. Now, in order to do all of this, obviously, we need a broad industry engagement. And I think, you know, from the Intel side, we really see, I mean, clearly 3GPP is, you know, the predominant body, you know, to define the overall networking stack. Obviously, ORAN plays a very important role. ETSI plays a very important role in the field of you know, of certain components that are complementary to what 3GPP does. And Intel can actually provide components and software to support this this vision on a future ecosystem. And furthermore, I mean, this also requires business and regulation relationships going through open source communities. We need to look at regulation. We need to look at interoperability and the like. Now, when looking at the space that Intel is covering, we are of course engaging in a number of partnerships and looking at key research areas. As I said, you know, artificial intelligence is really a key on this, but also security and privacy and trust is very important. I mean, you name it. I think none of these items here will probably really surprise you. Now, what I would like to share with this presentation is also a kind of list of top 10 technologies for integration in 6G systems. I mean, for further discussion, right? But we believe, you know, that that many of these items that are on the list here are really going to be key for the definition and design of future 6G networks, right? I mean, just to name a few. I mean, it is very clear, as I said. Let's look at item 2, that we need to go towards AI native design. So be it on the air interface or the network. Or, you know, item 4, for example. I mean, we are currently seeing the fight for additional spectral resources. I mean, that's very important because the overall communication system gets highly efficient, you know, gets really to very close to the theoretical limits. So what you can do in order to increase capacity, right? I mean, you need additional spectrum. It's very, very important. Just a thought on item 6, you know, from my side, you know, clearly, I mean, there's still lots of work to do on massive and distributed MIMO. You know, the challenge here is really, you know, that this is somehow intransparent to the user. So if you ask the average, the average end user, what do you think of MIMO? Do you like it? But probably it's very difficult to get an answer. So that is why, yes, we need to further improve the network efficiency, but we also need to keep an eye on the needs of the end user. And I think it's very important, for 6G that we define a system that provides a clear differentiation, like a sensible differentiation to a non-expert end user. Within the European ecosystem, we are now seeing that Europe is introducing a number of key regulations in order to actually put some guardrails onto these new upcoming technologies. And this is really important, because we have seen, that, for example, in terms of cyber attacks, things get more and more challenging. In terms of, for example, AI regulation, there are lots of discussions, that you can do good things, but also bad things based on AI. So I think we need to put, some guardrails, some framework, in order to make sure, that the things we are doing are really for the good for society. And this is what is currently happening. And I think this is giving for us as like technologists and researchers really a very interesting framework, because we can take these high level, like almost political requirements and think, what does it really mean technically? Just to give you an example, on the draft EU AI Act, one of the requirements is, for example, to avoid undesired biases. So on a high level, everybody agrees, right? Biases are not good. But what does that actually mean technically, right? How to measure this? Yeah. And this is not like radio requirements, where you can connect a spectrum analyzer to your device and see whether yes or no you meet the limits, right? This is functional, right? How do you validate this? Very, very interesting questions to the community. So as I said, these regulations are currently in the phase of being implemented. And really, I can only encourage the community being present here in the call to participate, because I think this is very, particular to the European ecosystem. We have the so-called new legislative framework, the NLF, which allows all stakeholders, including industry and academic stakeholders, all stakeholders, to contribute to the implementation of the regulations through the standardization process in the European Standardization Organization, so ETSI, CEN, and CENELEC. So, just a call, please get engaged. And if you want to have a little bit of additional background on how all of this works, please have a look at this paper we have recently published at the IEEE Communication Magazine. These are some references. And that's it, Ricardo. And I close my talk with this small hint to some legal notices and disclaimers, which I'm obliged to do. Thank you very much for the opportunity, Ricardo.
Thank you very much to you, Marcus, also being very much on time. So I didn't see any question in the chat, but I encourage the audience to ask questions in the chat. I have some questions, but I will keep them for the panel at the end of the presentations. So maybe we can move to the second presentation today, which will be provided by Marie-Josée Montpetit.
Ricardo, sorry. In the Q&A session, there is some questions, but because of the time limitation, Marcus, please also, if you can help to write a response in the Q&A session, please also do so. Thank you.
Okay, I will check. Okay. We'll address them online or at the end in the panel. So, okay, so the next presentation is from Marie-Josée Montpetit, who is a well-known Canadian researcher in distributed systems, in network computing, digital twinning, and applied artificial intelligence. From 2009 to 2019, she was a research scientist at the MIT, and She had numerous R&D positions in wireless networking industry. She is co-chair of the Computing in the Network Research Group at IRTF and adjunct professor at the École des Technologies Supérieures in Montreal. And finally, lecturer at the Télécom Paris Sud on programmable networks and at the McGill University. So I leave the floor to Marie-José.
Thank you very much, and good afternoon, everyone. It's morning here, but I'm happy to spend my morning with you. So again, I think the moderator mentioned a number of affiliations I have, and I want to make sure that these things that my presentation doesn't happen in a vacuum. And the COIN group at IRTF is very much at the center of all the research that's been done. Télécom Paris Sud, I teach there. ETS, I'm actually an adjunct. Ivado here in Montreal is one of the AI think tanks. There's a WireSci Center at Iowa State University where I can actually test some wireless concept directly on a test bed. And François-Xavier Deveilly is a member of the MILA here, which is like the great AI think tank, and is actually one of my collaborators. So thank you to all of them. So I don't want to go onto this thing, but in detail, I borrowed that from SoftBank. And I'm happy to tell you that I think what I'm going to say is very complementary to the first presentation. And in my world, the things that are very, very important are the sensing very much. The interfaces, and I'm going to come back to that, the AI functions, and obviously everything related to network and servers. And I think the last presenter also mentioned some of the social challenges which are beyond this. Well, obviously carbon zero or carbon free is one of them, and the AI regulations are also part of it. I work a lot, of course, in the technology challenges, and I am an architect. So I'm always looking at new ways to provide new services. My talk is going to be very much more focused on computing in the network, maybe than the previous presentation, and how computing in the network can actually be an enabler for data-driven networking, AI, and AI for the network and the network for AI. And I'm going to mention digital twins too. So again, that's what I want to present. The big thing for me right now in my work is this joint optimization of application and networks. And I think, again, the previous presentation mentioned it. And the common thread in network computing, this functional distribution, data-driven, joint optimization, machine learning and artificial intelligence, and especially federated learning into this thing, and digital twin, is, I think, a common thread for 6G in a way will be distribution, coordination, and federation. And those for me, I should make an acronym of this, DCF. I don't know, DCF means something else. So, but I think that is a very, if there's anything you keep from this presentation, it's this. 6G with computing and AI, it's distribution, coordination, and federation. So there's trends. Again, I don't want to go through all of this, but none of what we're doing comes out of a vacuum. Next generation networks have been there. People have been working on that for more than 20 years. AI, ML, and data-driven systems, the IoT and AIoT and sensing. And again, the previous presenters mentioned this idea of the fog edge cloud functional decomposition, distributed system. We all inherit from SDN, from computerized and containerized computing, and of course, green computing. We have to make sure that what we develop do not destroy the planet because it takes too much energy. So the idea here, and I think it was also presented by the previous speaker, but I would say when I teach, the biggest challenge I have is that people think that when you have an application on your phone, this is what happens. Your application talks to the web, and somehow some magical thing comes back. And what I keep telling my students is no, you have to think of the life of a packet. When a packet leaves your phone, where does it go? And this is much more, this cloud is much more like this. You have your Wi-Fi router, you have a first level of ISP, you have a core network, you have another transit network, and eventually you go to the data center where probably all your applications reside. So if you start thinking of this as this life of a packet, then there's a lot of places where you can start thinking about what happens to this in-network computing. And I will again, I think the previous presenter had this view of computing and networking getting together. I call it the network as a computer board and the internet as its operating system. And this is the environment we work on right now. So what is a little bit, I want to just tell people a little bit what in-network computing is. And basically, it focuses on the development of programmable data plane and programmable resources. We want, again, like was said in the introduction, we want to improve the performance of the network. We want to be able to identify critical events. We used to use, you want to use protocols and programming languages to abstract the functionality of the network. The PISA architecture that I'm going to come back to, and the P4 language were developed for that. I know there's a number of initiatives right now in Europe on what is called the network operating system. How do you define how you use the computing and the distribution of functions throughout the network? Your in-network functionality, you can do computing, you can do caching, you can do managing, you can do control and security. And I make a difference between functionality and applications. And the applications, of course, are data-driven systems, which are, you know, data is overwhelmingly being used for all kinds of applications, especially in IoT, in artificial intelligence, and in digital twinning. And again, I think the previous speaker mentioned how important it was to know how your AI is working and how it can help you with your application. Well, I think this is something that digital twinning allows you to do, and we'll come back to that. So what are the common requirements for the 6G intelligent data plane? Well, in a way, it's the joint optimization of networking, computing, and storage. You want to horizontalize the data plane because you want to cross-functional applications. One of my thing right now is to have what I call application-driven networking. And you can do that with network slicing. You know, you can essentially define that what an application needs. And again, I have access to a test bed that I can program in a way. And this is something that I think is going to be extremely important. It's the network as a service, but there's a very, very application-specific service. And again, you need, obviously, secure, it wasn't mentioned, I think, a lot in the previous one, but security and robust common semantics, because if you want to have your application drive your infrastructure and drive your network, you want to be able to make sure that everything is secure and as a common language. So in the beginning, we come back to this other thing. So this is our network. The basic applications of the in-network computing at the beginning was in the data centers. Why? Because they needed to distribute the workloads better. They wanted to be able to identify critical events. And they needed very, very fast computing because they wanted to do that, obviously, at line speed. So that was the beginning of in-network computing. And I was lucky that our group in the IRTF was formed at about that time, when in-network computing was this. But it created a huge amount of programmable network devices. Obviously, PISA, the flexible match action ASICs, previous speaker was from Intel. Intel at one point made a huge investment in in-network computing by buying the Barefoot company and integrate all the functions of the PISA into their systems. There's network processing unit, there's network interface card, CPU, FPGA, and all of this ended up being part of the network infrastructure. Before, this would be, maybe the first one, most of that would be computing. We wouldn't be really thinking of this as part of the network. And all these devices are programmed to tell us how to process the packets at different levels, but at the end, this is what they do. So this is just a shout out to the PISA. I don't want to spend time on this, but I think we cannot have a in-network computing talk without talking about this. It was the idea that you have a programmable parser on the headers. You want to do a programmable match action inside it. You can change the headers. You can change the direction of the packets. My goal is that I want at one point to be able to work on the metadata on this. You deparse and then you send back in the network. So you can enter with, going back to the data center example, you come out with the address of one data center and you exit and you're actually going to another one. Again, for people interested in this, is the P4. It's the language for PISA. It's a C-Lake. When you get the slides, you can look at it. It's actually good code. It's kind of old, but it still works. And you won't believe this. Now you can actually do P4 on Raspberry Pis. So this is all the background. Let's go back to what's happening in 6G. So the previous speaker also mentioned the importance of data. And somebody said, and actually it was related to me by somebody at Intel, but I don't know if the words themselves come from Intel, but data is the fuel of the 21st century. This is all where the knowledge is. This is all where a lot of the money is. And this is what we need in this 6G era to do the AI, to do the intelligent data planes. We need to have the data. So what happened next in this evolution? So what I said is it started here. But then people realized that these switches inside the network and these computers, they're very good to do telemetry. They see the packets go through. And we had a work with Columbia University, and the report was published in 2021 on the broadband trend. And the data was identified as the most needed research tool and technology in economics and in social science in the 6G era. Why? Because we need to predict performance, because we need models of broadband penetration, we need to add intelligence in the network. So the evolution goes there. Now we have the big fast switches in the data centers, but we have the local processing inside the nodes to essentially gather data on the performance of the network. Can we do better? Of course, because once we have all that data, there is something that I call AI for 6G and 6G for AI. So AI can help the network, but the network can help AI. So now we're going back to AI. So federated applications. Now that I have switches, well, I can probably add intelligence for the management. Well, how are these switches working? And then I can add intelligence a bit everywhere to decide what is the best path for my packets. Well, how can my application best take advantage of the rest of this network? Knowing that my application and the people who developed it are very aware that there are many ways that they can use this infrastructure and this architecture to make both the application more intelligent, to make, I don't think there is a Wi-Fi router that has a lot of AI right now, but I would love to have one of these so that when there's a power outage, my router knows that there is a power outage and can reconnect itself to something else. And there is more and more AI in network management. And we have a sister group in IRTF who's looking at network management. And we keep thinking that once you start having all that data on the telemetry, you know what the performance of the network is, you know what the delay, you know what the bottlenecks, then adding intelligence and federation of intelligence and reinforcement learning to know and to better predict anomalies in the network is well, it's the next step. So what's AI for 6G? Mesh federated agent in nodes, for managing traffic, control packets, to instantiate and update the nodes. This is actually, for people who are old like me, there was something when I was at university that was called active networking. It's a shout out to them, but it's something that can still be used, maybe not at a very important level, but you can update the node, you can send information there. And data packets can initiate their own operations. You can recognize through the in-network computing what a packet is. This is actually what we've been trying to do with identifying metadata and initiate some other operation that's connected to it. So that is the AI for 6G. And I guess the most important ones right now is the management of the traffic and the monitoring, the network management. But there is more than that. There is the 6G for AI. How can 6G with, more bandwidth, more flexibility, slicing, and all kinds of stuff, how can it help AI? So AI needs multi-source, multi-destination data captures, storage, processing, and the need for localized decision-making and automation. So, we're talking here of the XURLLC, and the previous speaker also mentioned, the distributed MIMOs and stuff. And we need support for distributed decision environments. I'm a big fan, and this is part of the research I'm doing in federated learning algorithms and data sets. And if you do not have a very good, reliable, and powerful network, you will not be able to do federated learning, because, of course, there will be some of your nodes in federation that will not be as covered, or maybe the bandwidth would not be there, and then you just kill your learning. And so you come to something that is also very dear to me in part of my research, which is digital twins. Why do you want to have digital twins? And you can put twins everywhere. So you can see that I'm building this network of intelligence, this network of computing. You want to model, simulate, and test the elements of your intelligent data plane. It's something to say, I'm going to put artificial intelligence into my network. It's another one to say, how is it going to work? And it's often extremely difficult to integrate artificial intelligence, even on a network element or a computer in a network, in an operational system. To do it at a smaller scale, well, then you don't get the scale. So what do? Well, in the old days, we were doing simulation. Simulation has a problem. It's not related to the real-time operations. Digital twins are related, are monitoring, and, well, are modeling the actual operation of the network. And there you can actually group several ones, and then a unified one, they can actually represent that structure. So you could say that every one of these twins represents the node to which it's attached. So you can completely resimulate or re-emulate and test the network. We had a presentation earlier in November, actually, when we were joking that the future of network testing in 6G with these intelligence, the intelligence everywhere, was that you would not send your equipment, you would email your digital twin, and you would email your AI algorithm, and you would just emulate it on your digital twin. And you can add all the computing there. So you can actually use your digital twin to observe and control the behavior of the network. You can actually verify that your computing is working well. You can verify the validity of your data, and your applications can also themselves be a twin and be part of the end-to-end optimization, which was, I'm saying, the joint optimization of the application and the network via in-network computing. So, in summary, how do you use intelligent data planes in the 6G era? Well, I'm some kind of a fan of self-optimizing networks. The reason being that for smaller ISPs who cannot afford large network management systems, it's easier for them to have a system that would be intelligent, that would use the telemetry that is measured through your in-network computing to manage a network, but also to optimize it. I think it's kind of well known that a lot of 6G mobile network will be extremely automated. Of course, artificial intelligence and machine learning, anomaly detection, again, through telemetry and learning over that data, digital twins. And there's a lot of, at Iowa State, we're also part of ORAN. So all the work that's been done on programmable intelligent RANs. And the next generation function virtualization and SDN, of course, everything is going software. And, you know, again, the previous speaker mentioned the incredibly large number of KPIs, but essentially what we're looking for, a lower cost for network operators, but at the same time, I would say a better user experience. So research topics, I'm a researcher. So again, joint optimization of network computing and application requirements, enable cross-functional and distributed applications, and cognitive intelligence linking the application and network. And again, for me, very important, especially when you do digital twins that actually query the data, and for anything that gathers data, secure and common APIs, so that we can actually get access to the data and get access to the data in a secure and private way. So it's my conclusion. 6G intelligent data plane. It's a programmable framework for advanced IoT and application-driven networking. We want to have a fog edge cloud, not just this idea that is a big cloud somewhere, we don't know what's in it. We want to be able to distribute, to take advantage of the distribution of the functionality, to have more advanced network services and applications that are based on, at the same time, enabling data, enabling AI and ML. And we want to have data combined with digital twinning to target service and advanced testing, deployment of application and services. Thank you.
Thank you very much. It's impressive how much the academic point of view is matching the industrial point of view explained by...
Yeah, but I don't think I'm a true academic. I think I work a lot with industry. So
Okay.
Yeah, it does match. And I think it's just looking a little bit further out. Like, I think the true optimization of application networks were not exactly there, but there's a lot of commonalities, yes. And it's a good thing.
Yeah, definitely.
I think there has to be a lot of interactions.
Yeah, absolutely. And I appreciate that you mentioned artificial intelligence as a way of reducing the cost of operating the network, which is important not only for the private network, but also for the mobile network operators. And that's a topic that Docomo is quite attentive to.
Yeah, I think it's one good thing of when, and again, it's a direct consequence of having all the data. But of course, you need to have the good data. But I mean, it's a consequence.
Excellent.
Thank
Okay, so there are some questions not answered in the chat, but I will keep them for the end, in the panel at the end. Some have been already answered by Marcus very diligently. Thank you very much, Marcus. So I would like to move to the next presentation. So I invite Baba-san to share the screen. So Hiroki Baba is a senior research engineer at Network Service System Laboratories in NTT. He has been engaged in mobile network architecture for more than 10 years, and he also engaged in design and planning of the NFV commercial introduction in the network of NTT Docomo in Japan. And currently he is working on 6G mobile network architecture, especially on the theme of in-network computing. So let's say that you will see that also the presentation of Baba-san is very much aligned with what we saw so far, and it shows many more details in terms of implementation and proof of concept. So Baba-san, the floor is yours.
Okay, so thank you for your kind introduction, Ricardo. It's my pleasure to join this seminar and give a brief introduction of our works. So, and hello all. My name is Hiroki Baba from NTT, and NTT is a Japanese telecom operator in Japan. And also, I am a senior research engineer there and mainly engaging the R&D regarding network architecture as introduced by the Ricardo. So today, I'd like to introduce our research regarding in-network computing and today's topic for 6G network. And the title is In-Network Service-Aware Computing with Hardware Acceleration in 6G Network. So here's the, my presentation's outline. So before getting into the topic of in-network computing, let me introduce NTT R&D's network architecture concept towards 6G, which is called Inclusive Core. And then I will present in-network computing platform activity called ISAP and its POC activities. So let me start with the inclusive core. NTT NS Lab especially engaging 6G network architecture study called Inclusive Core. And so let me briefly introduce about it. We are seeing that when we going forward to 6G, the network should be the platform to realize various convergence and cooperation, not only inside of the network, but also the outside of the network. Maybe the convergence and cooperation would be some kind of unclear for you, but the typical example of this term are computing and network convergence. And also we are seeing that cyber physical systems and cyberspace and physical space should be converged in the network. And so, and you all may know fixed network and mobile network should be converged. And in addition to that, analog communication would be happening in the future. So those communication can be also converged and cooperated with the digital communication. That's a kind of the high-level concept of the inclusive core. And the unique point of this architecture concept is to put a contact point in the core network. So this point will provide the anchor function for the user mobility and heterogeneous access as the current mobile network is, but also it will be the synchronization point between cyberspace and physical space for CPS services, and also user identity management for distributed user identity and private data management. And also it can be the communication proxy or even more AI avatar on behalf of the user's communication. So we are promoting the research and developments to identify the common use cases or technological building blocks to implement this concept. And in the current inclusive core architecture, there are 3 main technical building blocks included. So first, I will go in detail about the in-network service acceleration platform we are now investigating. And it will be presented later, so I would go in detail about this here, but I would like to briefly introduce other 2 things. One is self-sovereign identity platform. It is the data management platform based on the user's policy, and it can be used as a carrier ID wallet, which can hold user private data with a security. And also, we are seeing that conventional 4G and 5G network architecture, many mobile network operators have struggled about the signaling storm, and because it can cause a huge network failure. So for the 6G network architecture, we are currently seeing that establishing signaling platform, which is very robust and resilient. This is a key enabler for the 6G network architecture. And so as I cannot go in detail about the SSI or network robustness today, so please visit our website because we have published a white paper on our website. So you can see our study overviews and motivations related to technical trends. So let's move to the ISAP presentation. So I think, as you may know, and as presented in the previous presentations, I would explain, not go detail, but I would like to introduce our understanding for the computing and network convergence and its progress. So, it's currently cloud platform providing many applications on it, and some providers providing MEC platform to provide the 5G low latency services. But those platforms are very separated, and also 5G Core is running on top of the virtualization platform. And even if it is cloudified and it can run on the cloudified platform, but still virtualization platform still exists. And so for the RAN functions are still running on purpose-built hardwares for now. So going to 5G Advanced, we are now expecting the 5G Core and MEC will be all fully cloudified. But those platforms should be independent, so they are not sharing the platform itself. And the application running on the MEC will be widely deployed over the operator's network, but the application will work in a standalone way. So I mean that standalone is just running inside the MEC, not actually working together with other site or hyperscalers platform. So for the RAN, VLAN will be now currently starting to be adapted and over the network, and some of the VLAN will be cloud-based. So finally, in the 6G, we see that cloud computing resources will be widely deployed over the network, and the service functions collocate with the network functions as written here, and shares computing platform with them. So those network functions and service functions work in a distributed manner, meaning that a set of distributed functions work together to provide services on the distributed computing platform over the network. So I presented in the computing and network convergence in the beginning of my presentation in the Inclusive Core. It will be realized this kind of network configurations. And the same kind of the notion or proposal is now currently found in many organizations. And I understand that 160 is one of those groups, so maybe we are on the same page. So now I would like to share what kind of the pain points that our ISAP technology would address and its features. So first, on the left lower side, currently computing functions located UE devices and application servers and edge servers, not in the network. So this means that network, user equipment, and application servers works independently and not works in a tight coordinated manner. So it is not possible to work together with a tight coordination. So for example, it is not quite possible to require the performance in remote actuation in the manufacturer use cases. But now, this is good now, but when we talk about the extreme services expected in 6G, this would be an issue. So ISAP offers the in-network computing as a service, which integrates network function and computing functions. And it's ISAP complements the service functions in a distributed environment and intermediate them to provide the tight coordination of the application service and network services. The second part will be the shared resource with the software functions. It is obvious that software-based functions on the shared resource couldn't guarantee expected high performance requirements of extreme services with continuous deterministicity. So for this issue, ISAP enables E2E distributed computing using high performance accelerators such as DPU or GPU or FPGAs. So in the ISAP, multiple types of dedicated hardware accelerators are connected to process a very computing intensive tasks. So here is the brief overview of the ISAP architecture. It consists of two parts. One is the control plane, the other is data plane for computing services. ISAP control plane function integrates events occurred in the mobile core network and UEs, and also it integrates the events on the service application side. And that enables to orchestrate network functions and service functions together with the serverless framework. So for the user and computing plane, as shown in the slide, multiple accelerators are configured and chained. And networks and service functions are processed in a chain of accelerator hardware functions. So it contributes high speed and deterministic network and service function processing performance. So here is the architecture diagram just for reference. So in our proposal, ISAP control plane function should be integrated in the mobile core network to manage computing services. So it can directly interact with the core network shipplane, also LAN shipplane. And going further, it also directly works with the UE's shipplane part, and it will enable the distributed computing over the ISAP platform. And for the data plane, it would be on top of the user plane function of, so which is UPF, and which is resides to it. And it collocates the platform with network function and computing function. So by doing that, it can eliminate the duplicate packet header processing to forward the data from network function to computing function inside the node. And also, furthermore, it is aimed to avoid multiple protocol processing for inter-node communication. So I would explain some overview of the C-plane and U-plane function respectively in the later slides. So first, for the C-plane part, ISAP C-plane function provides service and network convergence in orchestration by integrating service and network events. So as shown in the slides, network events such as network registration or authentication or session establishment, those events are occurred by the user's behavior. And also the service event information such as authentication or video player start or stop or AI analysis or start or stop, those kind of the events are collected in the service event control platform. So by linking those events, ISAP trigger in-network computing resource instantiation for users, and the computing resource should be suitable for the user. And the network and computing resource configurations are also provisioned based on those events. So service and network convergence control is enabled by the extension of the SBA introduced in the 5G. So we see that SBA is a good way to flexibly integrate the events between different domains. So as you can see here, user equipment control plane and LAN control plane can send the control messages directly to the ISAP control plane, in not only about the core network plane. And also the cloud service control should be integrated in the ISAP as an intermediate controlling function. So SBA architecture should be able to link network control plane and service control systems. That's our view for the C-plane part. And for the accelerator part, we adapted the accelerator hardware chaining for the ISAP data plane part. It means that both network and service functions are offloaded to the accelerator hardwares to achieve deterministic service performance through hardware processing, not on the CPU involvement in the pipeline. So as you can see here, RAM functions or UPF and also gateway functions, also in the application things are offloaded to the DPU or GPU or some other accelerators. Those are not processed in the CPU part. Conventionally, most of the software functions are deployed on the CPU, and some accelerating technologies is available for now, but delay fluctuations can be increased by the CPU processing because CPU or software-based function can be suffered from this interruption by the other workloads. And we actually evaluated the accelerator chaining performance in our lab. So the configuration is same as the previous slide. So we measured the latency for the UPF and VPN gateway chaining So for this configuration, network packet transmission delay or jitter will be significantly reduced with the ISAP. You can see with the ISAP, the latency or delay, it should be the 0.15, and the jitter is 0.02. So very low. And also, not only the network transmission, we also evaluated the service processing delay or jitter using the video data stream processing with AI workload. So as you can see here, latency is slightly decreased, but you should focus on see the jitter side. So jitter is originally 13 milliseconds, but with the ISAP, it was 0.6, so significantly reduced. So now I would like to introduce about the POC activities with the ISAP. We actually trying to test our architecture realisticity and validity on using our lab, and we actually implemented the ISAP control plane on the cloud, and also some accelerators are used to offload UPF or RTP header handling or applications such as AI inference or 3D rendering of the metaverse application. So I would like to introduce some of the demonstration of these applications. So let's start with the first one. The POC number one is about the end-to-end hardware acceleration. So we see that we evaluated that how the application should be should we work on the accelerator chaining. So as you can see this video, you can see the video is collapsed on the left-hand side, but the right-hand side is with ISAP hardware chaining, it can work very smoothly, and AI analysis for object detection is works well. So what is the difference between those two? The difference is CPU involvement in the service and network function processing. And in left-hand side one involves packet forwarding, and RTP header handling is done in the CPU. And after that, the data is transferred to the GPU to analyze the object. But the right-hand side one, there's no CPU involvement to data transfer. So that's the difference, and it makes a significant difference. And the second POC is the service and network event-driven in-network computing control. We actually use the Metaverse application to integrate in the ISAP. So as you can see here, now users now accessing to the internet, and they are accessing the communication-based Metaverse space, but it is enough. So just having the conversation or chat in the Metaverse, it is enough to use internet-based services. But after clicking this SSI button, the Metaverse space will be changed, and the user transferred to another Metaverse. In that time, the GPU resources are allocated for this different Metaverse space, because this Metaverse space has a lot of complexity and complex 3D model, and also many videos are composited in there. So as you can see here, the GPU resources are going up. So it means that users' dedicated GPU resources are allocated in conjunction with this user session. And so users now can access to the Metaverse space, and he can see the many videos are included in the Metaverse space. And finally, he reaches some space to see many videos are composited in a space. So that requires a huge computing power in the network. But those tasks are offloaded to the GPU with on-demand requirements. So this POC is actually done with the Nokia, and the Nokia 5G core is used to collect the network events. So NEF-based interface is used to trigger the offloading application function to the GPU. And we've actually successfully finished the POC, and we proved that ISAP and 5G core works well to control in-network computing functions. And features confirmed through this POC, you can see that 3 points are confirmed. One is computing resources are allocated to in accordance with the mobile communication status of the device. And the second one is computing resources are allocated according to the service status changes in the cloud. And the last one is the dynamic control of the optimized computing resources according to the different characteristics of the mobile networks and application services. So in this metaverse case, GPU is used, but in the AI analysis case, DPU and GPU is allocated in on-demand manner. And the last one is 5G network slicing and in-network computing integration. So in this case, ISAP is used to link in-network computing resources to 5G network slice and 5G PDU sessions. The reason why we are doing this POC is because current 5G network slice can provide the guarantee for the network communication service only, not only for the service or application performance. So by combining the ISAP feature with the network slices, it can provide the application performance in addition to the communication service quality. So it means end-to-end SLA. So we actually did this POC using the public 5G core, and it's a live network, and the ISAP is integrated with the live 5G network to work with the 5G core, and it can allocate the AI computing resources, which is on the GPU, allocated based on on demand, and when the network slice is created, the GPU resources are allocated to the slice on demand. And this is how it looks like. So as you can see here in the left-hand side, AI video analytics on the prioritized slice works very smoothly because the network QoS and the application resources are allocated for this slice. But on the right-hand side one, AI video analytics would not work well and stops and starts frequently. So this is because the network resource and application computing resource are not dedicated, it's shared. So that's the difference between those two. So this is the concluding remarks. I would like to introduce an inclusive core for all. That's the entity's concept, but the inclusive core has a concept, includes the concept of the in-network computing as fundamental technologies. And for the ISAP, it is the platform to integrate network and computing functions for 6G, and sharing resources for network functions and service functions are controlled by the serverless-based event-driven orchestration. And we see that in-network computing functions such as C-plane port or D-plane port should be one of the core network functions for the 6G. And the last one, accelerator hardware. As I showed in my presentation, hardware acceleration and chaining for network and service are done in a pipeline of the accelerator hardwares. So function offload to accelerators and lower layer protocol between them used. So for example, RDMA or DMA to chain accelerators. And we see that now there's many accelerators available in the market, but it should be open API or SDK to put many types of workload with regardless of the accelerator vendors. So one of the possibility to commonize it is the open source community to work on those open API or SDKs of the accelerators. So that's it from me. Thank you for your attention.
Thank you very much, Watabe-san. Very interesting presentation. Also giving some numbers in terms of latency and jitter that can be achieved by using accelerators in the platform. So Regarding the questions in the chat, many of them are already answered by the speakers. Thank you very much. This makes my job very easy today. Regarding the presentation of Baba-san, there is one about the white paper title. So if you can answer in the chat, Baba-san, providing the title of the white paper of about inclusive core.
Oh, okay. Yeah, I will do that soon.
Thank you. And then there is one not answered that I will anyway use in the final panel. So thank you very much again, Baba-san. I think we can move to the last speaker of today, who is Professor Franco Calegati of University of Bologna. He's a full professor of computer science. Research interests are in the field of SDN, software-defined networking, and network function virtualization and cybersecurity. He also served as co-chair of the education committee of the IEEE SDN initiative, and he was director of the Center of Industrial Research in ICT of the University of Bologna from 2013 to 2019. I see that you are already sharing
Yes.
the slides.
Riccardo. Good afternoon, everyone. First, let me thank you and all the 1CG team for this invitation that I really appreciate. I will try to follow my previous colleagues, just providing some examples of how the concepts that were somewhat mentioned and described can be useful for a very specific vertical sector, that is the manufacturing sector. We live, University of Bologna is in an area that has a very, very strong manufacturing location. We have a lot of companies that makes more or less everything. And we try to apply some of these concepts starting from 5G. So some of these results are actually 2-3 years old, in order to understand which could be the benefit of an intelligent user plane and of some computing capabilities inside the network for manufacturing. First of all, starting from the very strong peculiarity of operational technology networking. Many of you probably know this, but it is worth mentioning anyway. OT didn't have any networking up to some years ago. The Industry 4.0 paradigm made such that most of the current manufacturing plants are connected. But the OT networking has some important characteristics that are related to the characteristics of the operational technology environment overall. In particular, the three issues that I'd like to mention that are, in my opinion, most important are the operational continuity. OT is a production system, and therefore, from the point of view of the owner and of their operators, of the people that work on it, it is of paramount importance that it keeps working. So everything can be done in this environment to keep the system working, and it is very difficult to explain or to convince anyone that it is worth stopping it to learn something. So this is an environment where everything that has to be experienced or tried or studied must be done in vitro. There is a very important role played by digital twins in this sense that were also mentioned. Moreover, OT systems interact with the physical world. Therefore, it is very important to realize that any malfunction, and most of all, every possible cybersecurity attack may result in real damages in real life, even to people above goods. Last but not least, OT systems have a very long life cycle. They keep working. If they work well, nobody's going to touch them. So they can be in operations for decades. So a much longer life cycle when compared to IT. These characteristics are such that especially intelligent networking in general or advanced networking functionalities are not easy to be introduced in this world. Therefore, we cannot rely much on the endpoints. We cannot rely much on something to be done in intelligent terminals and stuff like that. If we want to do intelligent tasks, we need to imagine that they must be put inside the network in some way. And that is why the intelligent user plane and the network computing may play a very important role in this case. I will show you 4 examples related to 4 projects that we developed in the last couple of years. The first one is related to quality of service. We made a study case with a project that I will mention in a second of exploitation of the capability to change the quality of service, or the bandwidth basically, of a wireless PDU session in a 5G scenario, in order to change the guarantee, the quality of a communication for specific tasks. And the use case was remote maintenance. This is the project I'm mentioning. It was called the 5G Connect. It involved a number of companies, and some of these companies, for instance, the first 2 you see here, or this one, I'm sure you don't know them because they're not worldwide known logos, but these are companies that build from components to factories. So all the span from little pieces, electrical motors, engines, to big plants that do ceramics, bottling and stuff like that. And they were very interested in understanding how they could use new networking technology for specific tasks. And the big issues was the integration between the logics of IT behind the network and the logics of OT that was pretty much composed of stupid devices. We adopted, to demonstrate what could be done, the concept of an asset administration shell. That is a concept that comes from the Industry 4.0 German initiative. That basically, for those of you that don't know it, is just a sort of software wrapper that emulates in the digital world a real asset in the real world. And what we did was basically to combine the digital representation of the operational technology assets with the digital representation of the network. And in the end, we got interfaces to a system that could combine what the operational asset was doing with the communication that it was using by doing it. In particular, just to give you a very simple example, we did something for demonstration purposes with cameras. And in practice, what was happening is you were supposed to connect to a camera that was monitoring a process. And in some cases, you could discover, like in this case here, that the camera was not providing a good quality of the image. It was actually very slow because you were missing bandwidth. Therefore, you could ask your system to change the bandwidth. So your user plane could change the PDU session you were using, asking for more bandwidth. And in that case, you could get a much better quality of the image, as you can see here on the right, thus going into the direction of fulfilling the requirements of the task you were going to do. But the camera is just a caveat to show that you could change the quality of the communication. It was not really related to any specific operational service. In practice, as you can see here, it was just recording what was happening in the data center. Something similar we did with the concept of composable enterprises. It was mentioned already that there is a trend towards containerized applications for complex tasks, both in manufacturing and in the IT. And what we did was demonstrating that with the concept very similar to the previous one, was possible to build a containerized infrastructure that quite automatically, again, using the concept that we saw before, could include new components that were able to change and to modify the connectivity of a certain functionality in order to fulfill some specific objectives. In this case, what we studied most of all was trying to understand how much time was required to do this, and whether it was really possible to obtain the goals. In this case, you see there is a communication at a certain speed that is shifted onto a 5G slow speed that is then shifted to a 5G high speed. And basically the goal was to demonstrate that the signaling on the intelligent user plane was compatible with the application requirements. In practice, it required a few hundreds of milliseconds, so well below a second overall. This is the timing needed to shift the PDU from the data flow from legacy network to a PDU session in the 5G or whatever. This is the first part. The second part of the presentation, in which I will also show you some works that we are doing related to the manufacturing world, is exploitation of P4 programmable switches. Again, OT application use legacy protocol and most of all legacy devices, and have very limited support of advanced networking features, as I said before. If we look, for instance, at the case of cybersecurity, this means that you cannot rely on very advanced features, and in a cybersecurity attack, as I mentioned before, can be extremely damaging for the operational continuity and because of the interaction with the physical world in an environment like this. Therefore, we assumed that we could embed in the network some functionalities that could help enhancing the reliability and the cybersecurity or legacy systems in the OT. In particular, this example, this is a very recent work that we developed in our lab. We take P4 devices, these are virtualized switches, that are equipped in such a way, programmed in such a way that they can create encrypted tunnels regardless what the end user are doing. So in practice, we assume that legacy devices, in this case, are Modbus clients and servers, must talk together. They don't know, they don't even know about cybersecurity. Surely they don't know how to embed cybersecurity in the tasks. And this embedding is done by the network, regardless what they know or what they can do. Therefore, the switches take some packets. These packets are encrypted and are sent over an encrypted channel, assuming that the encrypted channel is the part of the network that is supposedly vulnerable to possible attacks by external users. The interesting thing is that, this is more or less the flow. Here we actually try to compare this approach with the legacy technologies, because Modbus is a very old protocol that is usually in clear, but can be enhanced with TLS. So if you use Modbus over TLS, we have the workflow that you see here on your left. If you use Modbus in our environment, you have the workflow that you see on the right. The interesting thing is, if you measure the end-to-end performance of read and write operations in the OT, so you just watch what happens at the microscopic level in the working environment, you actually don't see a significant difference anyway. The performance are all very similar. TLS is the one that behaves slightly worse, but that is not really the matter. The matter is that in network encryption provides security more or less with the same performance of TLS, so of end-to-end technology, and very, very slightly worse than nothing, than in clear. Last, we also try to understand which could be the interplay between in-network computation and more advanced functionality co-located with network devices. That is another topic that has been mentioned, another solution that has been mentioned by my previous speaker. We assume that before enabled again, a switch can be co-located with more advanced processing functionality that can host a control plane and artificial intelligence capabilities. in this case, imagining to make all the data traversing the switch to the IE for detailed analysis is not credible because of the overall computation burden would be huge. So what we did is we implemented simple monitoring functionalities directly in the data plane using P4, and only in some specific cases when something anomalous was detected, we triggered the data plane to pass the data to the artificial intelligence in order to have a more detailed and more refined analysis of what was going on. Again, the goal was towards cybersecurity, in particular distributed denial of service attacks. The overall architecture is something like this. We, in practice, implemented a sketch, a count mean sketch, an asymmetric count mean sketch, counting into the P4 switch using the P4 program. This is it's very simple and very coarse way to measure the number of packets, for instance, between two endpoints at some level, for instance, IP or port numbers or whatever. In our case, it was at IP source and destination. And when this counting for specific couples of endpoints was overcoming a certain threshold, we forced the switch to pass all the traffic to a convolutional neural network that was providing a more detailed, a more refined analysis in order to understand whether that particular traffic flow was legitimate or could be an attack, even correlating different flows and so on. And again, the interesting result is that the performance we achieved turned to be very good. Here we have the representation of the precision, recall, FF1 score, so the performance measures of the artificial intelligence, of the detection. For those that are not familiar with these measures, what is important, they are as close as possible to 1. So the interesting area of values is the one that is circled in red here. So this is the detection capability of the artificial intelligence over the traffic that, as you see, can be very good for some specific values of the threshold implemented inside the network in the coarse computation. And on the other hand, on the right, you see that for those values, we get very good detection capabilities, but we pass to the artificial intelligence a quantity of data that is more than half the one that would actually really traverse the switch. So we limit a lot the amount of work that's supposed to be done thanks to the coarse computation that is done directly in the switch. So the message is the joint effort of the two components, so the one that you see here in purple and the one that you see up as a neural network, provides very good performance, almost optimal, with an overall computation burden that is significantly reduced in the artificial intelligence part, thanks to the pre-activity developed at the switch level. So in conclusion, this is the last case, okay, more or less in time. In conclusion, I can say that operation technology is a very interesting vertical use case for these specific applications, that there is a lot of interest towards intelligence user plane in the manufacturing environment, because the problem of the remote maintenance and remote update and so on is extremely significant for this environment. And the idea of being able to use a network that is ubiquitous, because the technology should be the same all over the world, more or less, and allows you to program, to decide with a certain freedom what kind of connectivity you're going to have at a certain time, it could be very, very important. At the same time, in network computing, may provide solutions for a much smoother transition towards a full connected factory, even in the presence of legacy technologies that don't support or just partially support advanced features. The takeaway message, the most important takeaway message that I see, that was mentioned in the previous presentations as well, is to enable the end user with customizable in-network primitives. So let's give the user the possibility to customize the network usage they're going to have, because I believe that this, if it happens, can be a very interesting applications for and market for future networks, in particular, say 6G, of course. Last but not least, let me just mention all the components of our research group that contributed to this, to all these works, and in particular, Professor Marco Prandini, Andrea Melis, and my older colleagues, our PhD students, and the many young research associates that were challenged by these interesting works. Here also listed some relevant publications, and I think that this concludes my talk.
Thank you very much,
I'll give the
Franco.
floor to you, Riccardo.
Thank you. So we saw also the perspective of the private networks for industry 4.0. That's very interesting. Of course, it's part of the use cases that we may consider for intelligent user plane, especially for automation of the management, which is one of the things that are considered like an issue from the industry point of view. Okay, so I think we can move to the panel. So maybe I will ask the speakers to enable their videos. And so there were many questions, and thank you to the speakers for answering them, but maybe some of them are meaningful to be answered also in this final panel. So one question that was not answered is related to which technologies need to evolve or change to enable efficient in-network computing with reasonable time to market. So I think that some of them were mentioned in the presentations, but maybe I don't know if somebody wants to stress again the point of which technologies need to be evolving or changing to support in-network computing in commercial deployments.
I can try and answer to that one.
Thank
I
you.
think it's everything that's related to controllers which have no open interfaces right now. So, and especially, I would say because it was a question to me also, especially at the lower layers. Of course, there's Open RAN that's looking at a lot of things like that, but I would say even for the industry, the last presentation, a lot of industrial controllers do not have interfaces. So it's really hard to get access to the data. It's really hard to get access to the controllers. So I would say the evolution of the controller towards more open interfaces is I think very important.
Yes,
Franco, you probably agree with that.
I completely agree. That is the point. We have many in-network technologies already available. Some closer to hardware, some closer to control plane and software. But what I see is still missing is some sort of common access to them. They are all technologies that still need a very high expertise. And it's very difficult to bring them to of course, not the general public that they never use this, but even to general technicians is not easy. So in my opinion, that is key to have them this is an example that one of the projects I mentioned was exactly this. I mean, we were collaborating with people that work in designing manufacturing plants that are extremely complex. So that these are smart people, but they're not experts of networks. Providing them with the capability to manage themselves, some of this concept is really hard, because you need to become a network expert. If you're already an automation expert, becomes difficult. You have to start again from scratch.
Thank you. Maybe I will just change a bit the question from the word technology to standard. So my question for the panelists is, which SDOs, so which standardization organization should be involved in creating a framework to support the network computing and intelligent data planes, and also which open source initiatives could be involved? So many were mentioned during the presentation of Markus and also Baba-san. So maybe can we again go to that point?
Yeah. Can I say something?
Yeah,
on that,
please,
Ricardo?
Markus. Yeah.
Yeah. So I think, as you said, I believe there is not like one target SDO or standards development organization, right? That would cover the whole scope, but we need to really look at the ecosystem, right? So we have, for example, 3GPP, where you definitely need to influence when you want to put new functionalities and features into the networking stack, right? For example, then for example, if you want to address requirements being outlined by the European AI Act or the European regulations on cybersecurity, you need to go to the European standardizations organizations like ETSI, CEN, and CENELEC, right, where the different related mandates are being addressed. When you want to look at open interfaces, you probably need to go to ORAN and so on. So basically, the point is you really need to have the ecosystem inside and clearly identify where to put which type of requirement. Ricardo, thank you.
Thank you very much. I don't know if other panelists would like to add anything to this point.
Okay, I would like to add one thing. So
Please.
yeah, as I mentioned in my presentation, open source committee could be a can contribute to the in-network computing, because in network computing context, there's some need for the distributed OS across the data center, and the Linux could be more enhanced to support the distributed workload. And also, as I mentioned, in the accelerators should be more used to support the network computing workloads. But those accelerators are now vendor-specific interface. There's much knowledge have to be learned for the developers. But by developing the open interface on the accelerators, the operators or service application providers can easily implement their application on the in-network computing platform. That's a thing I want to add. Thank you.
Thank you very much. Yeah,
I
please,
have another
Marisa.
point. I had my hand up.
Yeah.
I'm on the verge of starting my own standardization body. I think what is necessary is standardization of data. Right now, whenever, even if we had open access to the the controllers, to everything, whenever we do it, the data comes in another format. I think what AI and common data plane need is a way to format the data in a compatible way. What created the internet is that there was a common set of protocols that were describing how the data goes through the network. I think we need the same thing for the basic data. How do you describe the data? What is the data? What is the granularity? How do you describe the granularity, the format? There's no real standardization body right now that looks at that, because they look more at like at the, even the W3C doesn't look at that. So I think, yeah, I was joking the other day with colleagues that, yeah, I wanted to have my own standardization body and look at standardization of data.
Okay, that might be an idea. Franco, you wanted to add
Yes, no, I
something?
was actually supporting what was just said. One of the ideas behind the administration shell that I mentioned in my previous case is also this one, and we found that with experience that it can be really very, very useful, because if you have an instrument that allows you to access data on different domains or on different devices and aggregate at the level you like, it might be extremely useful. I mean, we found that on this issue from the end users, there is really an important response and feeling that they really appreciate this, because it's a need that is there and is usually satisfied with ad hoc implementations that at some stage show some weakness and you have to start again from scratch.
Thank you. So I would like now to ask another question, which is related to the previous one. So we understand that there are many open source initiatives and SDOs that will be involved in making possible and deployable at a global scale the technologies that were described during this panel, during the presentations today. But now my point is the economical justification. So how do we justify the huge investment in embedding computing in the network and having all these kind of, let's say, innovations in the data planes in 3GPP, for instance? So what are the applications that will require this, that it cannot be, which requirements cannot be fulfilled by the current 5G system? Some of them were mentioned. Maybe Markus can start.
Yeah. I think this is a very good question, and let me try to give some elements of answer to this. I think, you know, the point is there are services that probably can be provided on top of the network stack, right? And others, you know, may benefit from being integrated. And I think this is something, you know, what we still need to understand a little bit better. But let me give you some ideas, you know, that that may help to understand. For example, as I said in my presentation, you know, we really want to enable mobile network operators to offer, you know, AI-based services building on the available data and knowledge within the network, right? Do you believe, you know, that all of this network knowledge will be made available, you know, on top of the application layer? I think it's very difficult, right, Ricardo? If you want to access really this, if you want to capitalize on that, you need to integrate actually your functionality deep inside the network, right? It will not be exposed across all the layers of the system. It will be deep inside the network, right? Another point is, you know, latency, right? I mean, if you have time, you know, to, let's say, connect to the network and to go through the entire stack in order to have your AI application, okay, fine. Maybe that's the right way to go, right? But if actually, you know, you have highly latency relevant services, and you know, you can have a direct access, you know, to the lower part of the stack where your application is being executed and results are directly transferred back to the device. I mean, that may be highly beneficial. So it really, you know, it really depends on the needs you have, right, Ricardo? So I hope that this helps. Thank you.
Thank you very much. So trying to mention, please, Franco, go ahead.
No, sorry, Ricardo. In my opinion, one issue is also time. I mean, I'm pretty sure that many applications may benefit of all this and can be interesting markets, but I'm not sure how much it's going to take before it happens. That is an important issue, because the one example, one experience we had, that we started this project that I mentioned maybe 3 years ago, and we got at the end with apparently a very limited interest in the results we got from the companies we had aboard. Then now we are starting a new one with a huge interest, because in the meantime, they discovered that they really needed that. So final users, unless they really feel the need, they don't really bother about what is the novelty you bring to them. But when they do, they will be really interested in it. So I believe that there will be a market for these scenarios, but I have difficulties to say when it will be. And that might be a very important issue for the success of the technology itself, as you know.
Definitely. So now the point is, since these technologies will be developed in the upcoming 4, 5, 6 years and being available in the 2030s, the point is which kind of applications we expect to be necessary or are required by the society in the 2030s. So I don't know if somebody wants to elaborate. We saw some examples in the presentation from NTT, for instance, with 3D video streaming and I don't know if you...
Yeah, I can add something. We actually demonstrated the metaverse use case because it requires a huge computing resource. But why we choose metaverse for the use case of the in-network computing is because it is very common, but also it will be the common use case for the CPS or AI-based communication, which is told to be a common use case for the 6G. And we see that CPS, cyber physical system, would be one of the key use case for the in-network computing, because cyber physical system requires much of the sensor data or camera data, and those are aggregated in the data centers to analyze with the AI. Just analyzing AI is okay, it can be done in current architecture, but it feedbacks to the device or some other physical things in a real time. So it's the RTT requirements for those applications is very strict, and it cannot be done in the hyperscalers platform for the current architecture. So to realize the cyber physical systems in the real social infrastructure, we need to have in-network computing infrastructure to more real-time analysis and feedback actuation cycle. Yeah, that's the point I want to add here.
Thank you very much. So I think that it will be quite a complex scenario in the future, but there are interesting improvement and enhancements in the capabilities of the network that can be supported by using these kind of technologies. So I don't know if anybody wants to add anything.
I put in the chat the link to a draft that we're publishing in COIN on use cases.
Okay,
and
very
I
good.
think it talks, actually the video is there, but there's all kinds of other things. But I think another probably big application that may or may not be there that everybody will want to see is energy management. And I think with all the AI that's consuming a lot of energy, maybe there's going to be, again, this idea that, if you want to use federated AI, you need the 6G. You may need to have local computation and not just have to send everything in a huge data center that needs a lot of energy. So I think there's going to be that. But I just posted the draft in the chat, and you can have a look at it. There's a lot of use cases there.
Excellent. This is very important to know what are the use cases that require this kind of technologies. And so I guess that the audience will be interested to download this. So we have 3 minutes left. I have just one announcement to do about the next open lecture, but before that, I would like to ask the speakers if they want to make one final remark. I don't know if anything that you would like to stress again or... Okay, but I think we provided a lot of information today. It was very interesting also to me to learn about these technologies, and I think that we will follow up in 1CG with taking the suggestion we got today. So I would like to thank all the speakers. Thank you very much.
Thank you.
And just one thing. So I need to share my screen. And remind you that the 20th of June, there will be the lecture number 8, organized by 1CG. It's about cell-free massive MIMO. So please register for free on the website of 1CG if you are interested. And after that, I just have to say thank you very much to everybody listening today, and see you in the field.
Thank
Trying
you.
to make it possible what we saw today in the upcoming years.
Thank you very much, everybody.
Thank you very much.
Thank
A
you very
true
much,
pleasure.
everybody.
A true pleasure. Thank you so much. Bye-bye.
Have a nice
Bye.
evening. Bye.